Hey there, and welcome back to Calculus. In this video lecture, we're going to take a look at the material from section 2.2 on limits. You can see I've got the objectives of the lecture written there. I've got 4 objectives to accomplish with you guys here. I'm going to talk fast in this, trying to keep the videos as short as possible. Feel free, I hope you will actually pause these videos often, make some computations on your own, think about what I'm saying, because I'm going to be talking a mile a minute. And so my intention is for you to be pausing these things a lot and trying to fill in some of the gaps and calculation details that I go over quickly. Okay, so we have 4 tasks in this video lecture. I want to tell you, at least intuitively, what I mean by a limit, a mathematical limit. I want to show you that you can estimate those things using tables and graphs. We'll do most of our examples doing that. Once we've got that under our belt, I'll specialize off and tell you a little bit about something called one-sided limits. And then finally, at the end, we'll talk about something called infinite limits, which will look familiar to you if you've ever studied vertical asymptotes in pre-calculus classes. Okay, so just to motivate us as we get going here, maybe you recall that last time in both the tangent line and the velocity problems, it basically boiled mathematically down to the same thing. We had this expression, maybe it was the secant slope expression for tangent lines, or maybe it was the average velocity in the velocity problem, but we were interested in what the outputs of those expressions were doing when the inputs were near a certain value, and that value actually happened to not be in the domain. So that's kind of a commonality between the tangent line and the velocity problem, is that both of those things boiled down to wanting to understand what the outputs of a certain expression were doing when the inputs were near a number that we couldn't evaluate at directly. All right, so we're going to formalize that into a mathematical definition called a limit. And I have taken this from your text. You can see it comes from page 83 there. I'm going to try to square this up. I can kind of highlight us through this faster than I can write it. So what do we mean when we say that a function has a limit at a number? Here's the symbolism we're going to use for it. So we're going to write that set of symbols, and you can see how the author is telling us to pronounce it. We're going to say that the limit of f of x as x approaches a equals L. Or you can also say the limit as x approaches a of f of x is equal to L, or variations on it. Okay, but what does it mean? You have to have the function defined at least near the number a. So the author tells us, what does that mean? It has to be defined on some open interval that contains a, except this is an important exception. I'm going to change color. It doesn't have to be defined at a itself. All right, most of the limits that we're going to be interested in, we won't be able to plug a into the function f of x itself, but we want to know what's going on near a. So, okay, what does the author say? If we write that the limit as x approaches a of f of x equals L, what we mean is that we can make the outputs f of x as close as we like to the number L, arbitrarily close to the number L, provided that we take the inputs sufficiently close to the number a. All right, so the outputs of this function will get closer and closer to the number L as long as the inputs get closer and closer to the number a. And on closer and closer, we mean both sides of it. Okay, we don't ever insist that the numbers equal a, because again, a might, or the numbers x, the inputs, they don't have to equal a, because a might not even be in the domain of this function. All right, so that's what we mean by this notion of limit. So you can read there, I won't read it to you, but the author says, yeah, roughly speaking, it just means that these outputs are going to get closer and closer to this number L when the inputs are getting closer and closer to the number A. The author wrote the symbol up there for it. There's some different ways. You might use some shorthand. We might just write this and just say F approaches L as X approaches A. You can read that little arrow as approaches, okay? So there's just some notations for it, but that's the idea of a limit. Let's take our first example, again, clipping it from the text. The author has a function here, f of x. It's defined by x squared minus x plus 2. Okay, and he's drawn a little graph of it over there on the left in what's figure 1. And to ask the question, well, what's the limit as x approaches 2 of x squared minus x plus 2? Well, we could do it like we were doing for the tangent velocities. In this table here, you see that the author is taking a bunch of x values that are getting closer and closer to the number 2. Here in this column, they're getting closer and closer to the number 2, all from values that are less than it. In the right-hand column over here, they're getting closer and closer to the number 2 from values that are all bigger than it. But you can see in both cases, the output value of f of x is getting closer and closer to the number 4. All right. So you can see in the table that it looks like that limit is equal to 4. What are we looking at when we're looking at the graph of the function over here? Well, you have to imagine values of your function that are input values that are close to 2. I'm going to kind of highlight down here on the axis. Those are the input values that are close to 2. I was purposely trying to leave a little circle there at 2 because we don't insist that the number a has to be in the domain. So I'm looking at that little red picture that I drew down there is a picture of input values that are close to 2 but not equal to 2. And you can see in the picture, if you go up to the corresponding part of the graph, I won't be looking at f of 2 itself, but if I look at the corresponding part of the graph, let me just kind of draw some guides in here. What do I mean by the corresponding part of the graph? I mean the points on the graph that come from input values that are close to 2. Well, those input flat values are getting close to 4. And in fact, the closer and closer you get to 2, the closer and closer the outputs will get to 4. So you can kind of see that that limit is equal to 4 in that graph. You can see that the limit is equal to 4 in the table. And in the examples I want to do with you in this video lecture, that's basically what we're going to be doing is giving a function. I want to investigate limits using tables and graphs. All right, so I have to know what I'm looking at in that graph picture. I'm looking at what are the outputs doing. The outputs are values on the y-axis, right? So the outputs are over here. And those outputs are very, very close to 4 when the inputs are close to 2. All right. Before we get going on some new examples, let's kind of circle back through what we were talking about in our tangent line problems last time. The second example I want to bring up today, when we were looking at the slope of the tangent line, maybe if you remember the function, or you could stop this and go back and look at the video, but we were looking at that cubic function, f of x equals x cubed minus x squared minus 2x. And by playing around with tables last time in the tangent line lecture, we were able to guess that that limit, we didn't write it in this notation, but this is our new notation. We thought that those secant slopes were getting closer and closer to the number -1. So in our new language, or if you want to go back to that old video, this is the secant slope expression that we got to that function at the point 1 comma -2. And we noticed that those secant slopes were getting closer and closer to -1 the closer we took x to 1. Notice that x equals 1 is not in the domain of this secant slope expression, but we were able to still say what that limit was. Right? So the tangent line problem in this language, we were computing this limit. The limit as x goes to 1 of that rational function expression there. What about the velocity problem? Well, in the velocity problem, we had an expression for the average velocity. The average velocity over the time interval from 5 to t seconds was given by this thing that I've highlighted in the red brackets right there. And we took that average velocity as we averaged over time intervals from 5 to numbers that were closer and closer to 5. So that is, we took the limit of this average velocity as t approaches 5. And if you remember from the video, that limit was equal to 49. There were units on it here. I'm just going to leave it there, but it was 49 meters per second. 49 meters per second. Okay, so the velocity problem, we were really just computing a limit. All right, let's keep going here. I think I've got a total of about 8 examples in this lecture, so I'll try to go through them. Let's investigate the following limit. Okay, so I want to look at the limit as x approaches 3 of x squared minus 3x over x squared minus 9. Notice again that the number x equals 3 is not in the domain of that function. It doesn't have to be. I can take limits at values of x, the a value, that aren't in the domain because the limit is just about what's near it. So I've got 2 pictures, 2 graphs here. The one on the left is the graph of the function. I've labeled it there, y equals x squared minus 3x over x squared minus 9. But it's a little bit hard to see what's going on in that picture. So over here, I've just got kind of a zoomed in version of it. I can try to highlight, if you like, what we've zoomed in on. If I kind of color over here in red the portion of the curve that we're looking at, we're just looking at it over here blown up. So the y-axis is a little bit more visible. So I've just kind of zoomed in. The picture on the right is a zoomed in picture on the left, and I've color coded in red there. Okay, so let's use the graph first this time. So we're trying to say what this limit is. So I'm looking at values of x that are near but not equal to 3. So I'm always going to kind of visualize that as a little punctured interval around 3. I can get as close to 3 as I want, but I can't equal it. Yeah, and then I look at the corresponding section of the curve. If I go straight up from 3, I can see that on that corresponding section of the curve, what are my values getting close to? I'm looking at these things. I'm not looking at f of 3, but just close to it. And well, if your eyes are good enough, it's really small on that y-axis. You can see a y value over there that it looks like they're approaching. So that gives me some evidence that this limit looks like it's a half. What about the tables? Let me actually just sort of squeeze this down a little bit so we can see it all at the same time. Over here in this table, what have I got? On the right hand, or sorry, excuse me, the left hand side of this table in the X column, I've got a bunch of numbers that are approaching 3. They're approaching 3 from values that are less than it. Over here, I took a bunch of numbers that are also approaching 3. They're all bigger than it. The definition says we should check both sides. And looking at the output columns, it looks clear to me that in both cases, the numbers on the right are getting closer and closer to 0.5. So even though x equals 3 is not in the domain of this function, x squared minus 3x over x squared minus 9, we can say that it looks like the limit as x approaches 3 of that function is a half. All right, so I think it's probably a good place to pause and see if all of that made sense. I'm just going to move along here, trying to keep the video short. Let's take a look at another limit. This time I want to look at the limit as x goes to 0 of sine x over x. I hope that you are going to take a calculator, a spreadsheet, reproduce these tables. Don't just passively watch me. Maybe I've got errors in my tables. If you're going to use a calculator for the sine function, make sure it's in radian mode. Put it in radian mode for this whole course, because whenever I talk about the sine of something or the cosine of something, I'm always measuring the angle in radians. So here again, x equals 0 is not in the domain of sine x over x. You can't divide by 0. But we can ask, well, what's the sine of x over x doing when x is near 0? Here I've got my two pictures. The one on the left, I like it. It's a nice looking wavy function. That's the picture of sine x over x. And the one on the right is just a zoomed in version of it. This time, let me highlight the portion of the curve again in the same way. So I just took this part of the function and drew it over here so that we can kind of look at the scale a little bit better. Okay, so that's what I mean by zooming in. And if you look at that graph, if you take a look at values of x that are near 0 but not equal to it, notice whenever I'm talking about inputs, I'm looking at that x-axis. And then I'm wondering, well, what are the y-coordinates doing when I'm taking x in that interval? When I'm choosing x close to 0 but not equal to it, well, the y-coordinates look like they're getting closer and closer to the number 1. You can see that in the two tables down here. On the left-hand side, I'm choosing numbers that are getting closer and closer to 0 from below it. The outputs are getting closer and closer to 1. Here I'm choosing numbers that are getting closer and closer to 0 from above it. They're all positive numbers. The outputs are getting closer and closer to 1. So can you pause and say, what do you think that limit is? I'm just kind of checking to see if the notation and the vocabulary makes sense. It looks to me like the limit as x goes to 0 of sine x over x is equal to 1. Based on those. I'm calling these investigations or estimates because I'm not giving any mathematical proofs. I don't really have a rigorous definition of limit, but this is what we're going to content ourselves with at this level of our first calculus course. I just need you to be able to look at a graph or a table of values and estimate, say what the value of these limits are. All right, so pause it, soak it up. I'm going to move on to example 6. This one, I think we can get rid of the black bars on the side. So here we're looking at a picture of a function y equals sine of 1 over x. Let me write that in here. And I'm asking the question, what's the limit as x goes to 0 of sine of 1 over x? So I'm asking, well, what are the outputs getting close to? Outputs are y values as the inputs get closer and closer to 0, but they don't equal 0. So there's 0 down there. And if I draw a picture of the inputs that are close to 0 and not equal to it, I'm thinking about a little punctured interval around 0. And in this particular picture, Unlike the previous two, the y values aren't approaching anything. Uh, um, this picture is a little bit hard to read, but if you kind of read it left to right, what's happening is this wave, this sine wave, keeps oscillating between -1 and 1, but it's oscillating faster and faster. So as x approaches 0 from values that are negative, that thing just keeps going up and down between -1 and 1, faster and faster and faster. Same thing on the right-hand side. If as x approaches 0 from the right-hand side, the wave, it'll keep taking on values between -1 and 1, never skipping any of them, faster and faster and faster. So the output values of this function aren't approaching anything as x approaches 0. So the language that we're going to use when this kind of phenomenon happens is we're going to say that this limit does not exist. Does not exist, or you can feel free to use the well-trodden acronym DNE. This function doesn't have a limit at x equals 0. Its outputs are not getting close to any specific value as x gets close to 0, so it doesn't have a limit. So example 6 is teaching us that just because you ask the question, well, what's the limit as x approaches a of some function, maybe there's no answer. Maybe that limit doesn't exist. This is a very interesting example of a wave whose, what's the right word? Its frequency is becoming infinite as you approach, as x approaches 0. So the wave keeps bouncing back and forth. It's between its maximum and minimum values faster and faster. Okay, so a limit that doesn't exist. Let's move along here. Here I've got a function. I don't have a formula for it. I've just specified this function with a graph. It's called f of x. I've labeled it there, and I want to investigate the limit as x goes to 1. Okay, so let me draw in my usual way a little punctured neighborhood at 1. And I'm interested in, well, what are the output values of this function doing when x is approaching 1? It kind of depends. As x is approaching 1, say from values that are less than it, can you see that darker? Yeah. I can see that the output values on this function, the y coordinates, it looks like they're getting closer to the number 1. But as x approaches 1 from values that are bigger than it, so I'm looking at the x-axis taking values that are getting closer and closer to 1 from above it, it looks like the output values are getting closer and closer to 0, right? So, but the limit definition said that it has to happen from both sides. That as the input gets closer and closer to 1 in this case, the output values would need to get closer and closer to some single number. Well, it's not happening. From the left-hand side, they're approaching the number 1, and from the right-hand side, they're approaching the number 0. So I'm going to also say that this limit doesn't exist. It doesn't exist for sort of a less, I don't know, dramatic reason than the previous example. The previous example at near x equals 0, that sine of 1 over x function was just freaking out. But here, this function doesn't freak out really at x equals 1. It's just that what its limit is trying to be from one side, from the left, the function values are trying to be very close to the number 1. Yeah, do you guys agree with that? That the y coordinate at the tip of this curve here looks like it's about 1. But what it's trying to do from the other side, as x approaches 1 from values that are bigger than it, the y coordinate on the curve is about 0. And because 1 is not equal to 0, we can't say that those values are getting close to some single number. All right, so this function doesn't have a limit at x equals 1. The limit doesn't exist. But I don't think we should totally throw away the fact that it did have a limit sort of from one side or the other. So that's what this back up in the objectives when we were talking about one-sided limits. I think I've got the book definition ready for us to look at here. So let's just scroll down to where we can see it. This comes from page 88 in your text if you want to look at it in bigger font or something like that. But what do we mean by one-sided limits? So the notation is very subtle here. In fact, you can't really see it all that well at the resolution that I've got. But here the author is writing the limit as x approaches a, and then there's a little minus sign there. I'm going to write it in my handwriting to blow it up. So it's writing the limit as x approaches a. You read this from the left, as x approaches a from the left, or the left-hand limit. So what does it mean if it equals L? It means the same thing we mean for limits, except you only consider values of x that are on the left-hand side of a, or that less than it. So if you look down here in figure 9, this time I'm also going to be looking at a punctured interval at a, but I'm only going to consider values of a that are less than it. That's the left-hand limit. If you can see that font down there, it's small, I'll write it bigger. The limit as x approaches a from the left of this function is equal to L, all right? And likewise, we have right-hand limits. What does it mean to take the limit from the right? You can see in the author's notation there, sorry, that was the wrong color. What does it mean to take the limit from the right? I'll blow up the font a little bit for you. It's writing the limit as x goes to a, and there's a little plus sign. So you read that plus sign from the right. And what it means is that you restrict your attention to values of x that are bigger than a, right? So they come from the right. So this left and right is with respect to the x-axis number line. Numbers on a number line get smaller to the left and bigger to the right, okay? So that's what the author means by one-sided limits. So if we return to our example 7, we already said that that function didn't have a limit at x equals 1, but it does have left and right-hand limits. The limit as x approaches 1 from the left, can you pause the video and say what it is before I do? So if you're only considering inputs that are less than 1, what's the output of that function doing? As you approach 1, the output is approaching 1. The left-hand limit is 1. The right-hand limit of that function at 1 is 0, right? So those two limits aren't the same. So that's why it didn't have a limit, or now we'll call it a two-sided limit, right? So if you don't have one of these decoration marks, minus or plus, it means you have to consider both sides, right? So the minus and plus, one-sided limits, left-hand limits, right-hand limits. Maybe as just an observation, let's make a note here that the two-sided limit, down here I've got no plus or minus, so that's a two-sided limit. It would equal some number L if and only if the left and the right-hand limits are both equal to L. So if you have a left-hand limit and a right-hand limit, they have to have the same value in order for the two-sided limits. So this is a perfect picture to keep in mind of what it looks like for a left-hand limit and a right-hand limit to exist, but the two-sided limit doesn't. All right, pause, take a break. I know these videos are a little bit long, but in this it's just kind of better to put it all in one video so it's in one place and you can kind of stop it and digest as we go. All right, let's practice this business a little bit. So I've taken the next example, example 8 in this lecture. It was example 7 in your book. And I just want to practice these notions with you guys. So we've got a function here called g of x. It's drawn. The usual convention when you're drawing a function like this, the little open circle on the graph like this, means that that's not the y-coordinate for the corresponding input. This closed circle does. So g of 5 is whatever the y-coordinate is right there. Looks like it's a little bit more than 1. Okay. So just trying to use the scale to the left to the best that we can, let's try to answer some of these questions. I hope that you're going to pause the video and try to answer them before I do, and then you can kind of check to see how you did. But the first one is, well, I want to take the look at the limit as x goes to 2 from the left. That's what that minus sign means. So x goes to 2 from the left. So let me show you with my laser pointer what I'm looking at. I'm finding x equals 2, and I'm thinking about values that are approaching it from the left. And then I'm looking up at the corresponding part of the curve. That corresponding part of the curve would be up here. And I'm wondering, well, what are the y values getting close to on that corresponding part of the curve if x is getting closer and closer to 2? And can you say it? It looks like that limit is, what is that limit? The limit as x approaches 2 from the left of this function g of x, it looks like it's equal to 3. Yeah, the y values on this curve are getting closer and closer to 3 as x approaches 2 from the left. So what about from the right? the limit as x approaches 2 from the right of g of x. It's the same kind of phenomenon, but this time I'm looking at values getting closer and closer to 2 from values that are bigger than it. The corresponding part of the curve is up here. And you can see that that limit as x goes to 2 from the right is not 3, but it is, why am I pausing? I don't know, you're going to pause the video. It's 1. The limit as x goes to 2 from the right of g of x is 1. So I'm going to run out of room if I keep writing these limit things here. So I'm just going to start to write some answer. Well, actually, let me write it. So what about the two-sided limit? What did our little note just say? The left and right-hand limits both exist, but they're not equal. So the two-sided limit doesn't exist. All right, the two-sided limit doesn't exist. How about part D? What's the limit as x goes to 5 from the left of this function? So this time you have to bring your attention over here. Approach 5 from the left. Y values on the curve are getting close to 2. They're getting close to the number 2. That's the same as the limit as x approaches 5 from the right. And because those left and right-hand limits are both equal, I'm going to squeeze part F over here. The limit as x goes to 5 of g of x is also 2. Notice that g of 5 is not 2. That's okay. That's okay. The function's value at 5 doesn't equal its limit at 5. No one says it has to. In fact, when you take limits, the limit as x goes to 5 is completely independent. G wouldn't even have to be defined at 5. Like here, g of 2 doesn't even exist. G of 2 is not defined. There's no dot above x equals 2. So you can talk about limits independent of the function value is the point. Okay? You guys have any stamina in you? We have one more topic, infinite limits. Infinite limits. I'm going to take this from the text to make it go a little quicker. I'm converting it from example 8 to example 9. It's on page 89. The function that the author is talking about is 1 over x squared, and we're looking at the limit as x goes to 0. So we're looking at the limit as x goes to 0 of 1 over x squared. And well, you can look at the graph down here. When x is getting close to 0 from both sides, it looks like these function values are just getting bigger and bigger. You can see that in a table here. The author's got a sequence of points. He's writing plus and minus at the same time, but those numbers are getting closer and closer to 0. And you can see the closer they get to 0, the bigger the output of the function gets. So in this sense, this limit doesn't exist. The limit doesn't exist because the values are not approaching a finite number. But we are going to kind of write down something that indicates in what way they don't exist. So the author is going to write something like this. The limit as x goes to 0 of x squared, or 1 over x squared, excuse me, is infinity. So this is just another way of saying the limit doesn't exist, but it's kind of more precise. It doesn't exist in the sense that the values are getting larger and larger and larger. So that's what we mean by an infinite limit. It's not a number. Infinity is not a number. In fact, the author says this, and it's so important that I'm going to highlight it for you too. We're not treating infinity as a number. I'm not saying that it's some equal to some L value. It's just a notational way of saying that the outputs of this function are becoming arbitrarily big. Increasing without bound is another way to say that, as the inputs become close to, in this case, 0. Okay? So that's what I mean by an infinite limit. So you guys have been good sports. I don't know how long this video is, but it feels long. But let's look at one last example. I've got a function here, x minus 3 over x minus 5. And I want to take a look at the limit as x approaches 5 of that function. So if we start, say, on the left, as the values of x approach 5 from the left, values that are less than it, we can see that the function's values are becoming more and more infinite, but in the negative direction. If we approach x equals 5 from values that are bigger than it, we see that the function is getting more and more infinite in the positive direction. So looking at the picture, we can say that this limit doesn't exist. And we can't write that it's infinity or that it's minus infinity because it's kind of doing both. From one side, it's minus infinity, and from the other side, it's infinity. So we can write, and this will be the last thing, we could write some one-sided limits. They don't exist, but we could write something, for example, like the limit as x goes to 5 from the right of this function, x minus 3 over x minus 5, it's infinity. Yeah, the values are getting bigger and bigger. The limit as x goes to 5 from the left of x minus 3 over x minus 5 is minus infinity. So it'll always be the case. You probably remember in pre-calculus that when you have some quantity like x minus 3 over x minus 5, and its denominator, as x approaches 5, its denominator is becoming 0, but its numerator is not. Well, that such a quantity is always going to kind of become plus or minus infinity. It depends on the signs. And if x is greater than 5, the limit from the right, well, then x minus 3 will be positive, and so will x minus 5. So a positive number divided by a positive number is a positive number. So you're going to get a positive infinity. As you come in from 5 on the left, x minus 3, as long as x is bigger than 3, and it will be if you're close to 5, is still positive, but x minus 5 will always be negative. So that's why you're getting a minus infinity. So these kinds of limits, infinite limits, are sort of related to the vertical asymptote problem that you studied in pre-calculus. Okay, I'm going to stop this video here, so thank you for listening.